So, we have done some problem on pneumatic conveying, which you have perhaps seen and done at your home also. Now, let us go to another very important aspect, that is called Newtonian. We have seen till now all fluids were Newtonian, but if the fluid becomes non-Newtonian, right, then we call it to be non-Newtonian fluid flow. Right. So, we call it to be non-Newtonian fluid flow. Right. Now, to do that, let us recapitulate a little. Recapitulate a little in the sense, we had said that shear stress, right. If you remember, in many classes earlier, we had said shear stress, and in this non-Newtonian flow, when we will define what is the non-Newtonian, why we call it to be non-Newtonian, etc. Before we go into that, let us also look into this aspect, that a little recapitulation, that you remember we had said that if we take a bunch of cards like this is one card, this is another card, playing cards I am referring to, this is another card, these are all enlarged picture, right. In reality, by this term the whole card bunch will come out, right. But if we assume that this kind of cards are there, and then if we apply a force in here, force at the bottommost card, then what will happen? This card will move a little, right. Then the next card will move a little, then the next card will move, it should have been a little more, so that we understand it easily. Then the third one would have moved even a less, and the fourth one would have moved, might not have moved at all, right. So, we get a distribution of these cards, it looks like this, right, whereas originally it was like that. So, movement of it has occurred, the main card that remained, actually if we would have done it right below, then it could have been more easily understandable, that the first card moved like this, the second card did move a little, or the topmost card, this did not move at all, and next to that moved a little, next to that moved even like this, right. So, there would have been a movement like this, which we call this, right. This because we gave the force F. This card movement is the right example of giving the shear force, where the layers, by definition you see that shearing stress is a force that causes layers of parts to slide upon each other in opposite directions, right. an example of shearing stress is the force of two connecting rocks rubbing in opposite directions, right. As we said, the best example could have been the playing cards example, right. Now, when we are saying it, we remember that in couple of months or years, there were many earthquakes all over the world, right. There also the same thing happens. The two plates of the earth, they were on one over other. Suddenly, there is a movement, right. This kind of friction, movement is there, and one plate is trying to hold the other plate is trying to go out because of the force applied, and that made the whole earth making where this place happened, that place quake, or which we know as earthquake, right. So, similar to that, or if two stones are like this, they are one over other getting rather some force you are applying like this, that is called the shear force, right. The best example we have given with the card, right. So, this card example is the best one, which you can easily understand, because playing cards you may have in all the houses. So, you take that bunch, put a little with another very thin one, give a sudden force to the bottommost, and you will see that there will be a distribution like that, right. The distribution of cards will be like that. The bottommost which one you have given the force, it has moved a little, and then the next one, then the next one, like that, and maybe the top one did not move at all, because by the time it reached to the top, the force was nullified. So, it could not move. So, this kind of thing happens in liquids also, both in liquid and as well as in gaseous, or more prevalent in gaseous than that of the liquid, but still it is in the fluid, right. So, by definition we can say that shear stress means the component of stress that causes parallel layers of a material to move relative to each other in their own planes, right. So, these cards, if we consider them to be, each one of them to be one of the plane, right, each one to be one of the planes, then these planes are again this stress that causes parallel layers of the material to move relative to each other, right. With respect to the bottommost, the topmost did not move at all, the next to that moved a little, next to that moved even a little, like that it is happening. That is, the layers are moving with the force given, right. So, this is a relative movement of the layers when they are together, right, in different planes. So, keeping this background in mind, we now move on to the non-Newtonian fluid, flow through the non-Newtonian fluid. It is also a big one. So, hopefully may not be in one class, it will be over, maybe several classes will be required. So, as and when the time will permit, till that point we will continue, and maybe in the following class or next class we will do a little recapitulation and go on proceeding, right. Now, let us look how the definition says. Non-Newtonian fluid, this follows the power law equation, right. So, Newton's power law equation, that which we call Newtonian or non-Newtonian fluid, that relates that shear stress tau is equals to minus mu dV dr, right. So, this minus mu dV dr, this is the very simple relation of the fluid, right, as given by the Newton, and this the liquid or fluid which follows this relation straightforward, they are known as Newtonian fluid, right. They are simply known as the Newtonian fluid, and they follow this simple relation of the Paul law, right. There are two types of liquids like that. One where shear stress oblique, that is rate of shear stress to rate of shear rate, this relation is independent of time, This is one type of fluid, and most of the liquid and foods they follow on this type of relation, and the other that shear stress to shear rate, this relationship is time dependent, right. So, when it is time dependent, then another one type, for example, few salts, gels, they follow this type of relations, right. So, now these are the two, that is shear stress to shear rate independent of time, one type of fluid, and shear stress to shear rate is dependent of time, that is another type of fluid. So, one is time independent, another is time dependent. Means time dependent means at 11 o'clock, if it is one value, maybe at 12 o'clock it will have another value, maybe at 1 o'clock it will have another value. So, that is time dependent, but if it is time independent, then we will say at 11 o'clock whatever value was there of the fluid, same value is there at 12 o'clock, or the same value is there at 1 o'clock. So, this we have to keep in mind, that time dependent and time independent, meaning that shear stress to shear rate ratio, the value does not change with time, that is time independent. 11 o'clock, 12 o'clock, 1 o'clock, 2 o'clock, all the time the value remains same, then it is time independent. And if the value changes at 12 o'clock or at 11 o'clock or at 1 o'clock, then we call it to be time dependent, where shear stress shear rate ratio varies, right. Now, shear stress is this and shear rate is called this one, dV/dr is known as shear rate, and this shear rate shear stress shear rate ratio normally we call, why this negative? Because as the shear stress goes up, the shear rate goes down, that is why it is indicating negative. Exactly this is says that mu minus dV dr, right. So, this rate ratio is known as the viscosity, which we call as mu, right. For the Newtonian fluid we call it to be mu, right. So, let us go into those where it is time independent fluids and there are 3 types of such fluids, right, and these 3 types are known as Bingham, plastic, right. Then the other one is known as Bingham plastic, then other one is known as Pseudo-plastic, right, and third one is known as dilatant. Right. So, these are the 3 types which are time independent fluids, right, and all of them follow the power law equation. So, let us go back to that power law equation which we started with, that is tau is minus mu dV dr or mu minus dV dr, right. So, we said shear stress is proportional to shear rate, right, and this we said to be equals to a proportionality constant mu minus dV dr, right, and we also said that negative term implies that as the shear stress is increasing, shear rate is decreasing, right. So, and the proportionality constant we said it to be mu, or that is normally denoted as the viscosity, right. So, now as we said that Bingham plastic, this is unlike Newtonian fluid. Unlike Newtonian fluid, if we plot shear stress versus shear rate, tau versus dV dr, if we plot, then unlike Newtonian fluid, it is because this is Newtonian, we said, right. So, unlike this where it is shear rate and shear stress is as it is increasing, right, right. So, like this it is following almost 45-degree line, but for the Bingham plastic, it is unlike that this one where it is 0, starting from 0, then we dV dr, right, dV dr minus dV dr, with increasing of r, the V is decreasing, that is the minus negative, with increasing of r, V is decreasing, right. So, if we take this is the pipe, this is the center, if this is the r, so as r is increasing, rather we write this way, r is increasing, V is decreasing, right. So, we say that for the Bingham plastic, unlike this Newtonian fluid, you need a minimum threshold shear stress which is required. Once it is there, then it follows the similar way as it is in the Newtonian fluid, right. But that means you need the initial push, that let it start, then it will follow, right. Let it start, then it will follow. One of the example is that say your toothpaste when it is there. So, in the tube it is there, unless you put a press it will not flow, right. So, give a thrust to that, so that it flows and it starts flowing. So, that is what is required, and this is similar to the Newtonian fluid, but you need an initial stress has to be given, initial push has to be given, so that it moves like that. Generally, we say for many students that okay, unless and until they are giving a jolt, they don't study, right. So, a similar behavior can be said, right. So, Bingham plastic like that. Then here this we can relate in terms of shear stress as tau minus tau yield is equals to minus mu dV dr, where this tau y is the yield stress, that is a minimum which you need to give to the for the flow of the fluid. Once it starts flowing, then it follows the Newtonian fluid, right. Example is chocolate mixtures, or margarine. Margarine is a similar like butter. Margarine is a similar like butter, substitute of butter in many cases it is said, right. So, that is the margarine. Okay. Then grain water suspension, as we said, toothpaste, or it could be sewage sludge. Etc. In sewage sludge also you will see that unless there is a push, unless there is a stress given, unless there is a force given, that sewage sludge also does not move, right. Same as we said for the toothpaste. So, in the toothpaste you give a pressure, then it comes out from there. So, that is the yield stress or tau y which we are referring to, right. Same is true with chocolate mixture, same is true with margarine, grain water, suspension, sewerage, etc., right. So, it follows this relation that tau minus tau y is minus mu dV dr, or this is called the shear stress versus shear rate relation for the Bingham plastic fluid, right. So, next we go to the second type, that is called the pseudo-plastic, right. For pseudo-plastic UDO, for pseudo-plastic fluid we write the relation as tau is equals to K dV dr with a negative, right, to the power n, right. Say this is equation number 2. Here n is less than 1, right. Here n is less than 1, and most of the non-Newtonian fluid, most of the non-Newtonian fluid follows this relationship, right. So, there the general power law equation can be written like this, right, and this is commonly known as Oswald-Day-Weyl equation, right, where K is the consistency coefficient or index and N is flow behavior index. Right. The unit of this K is there. It is Newton second to the power n by meter to the meter square. Right. Newton second to the power n by meter square, and n is flow behavior index. Right. Apparent viscosity can be obtained from this equation 1 and equation 2 as mu apparent is equals to K into minus dV dEr to the power n minus 1, right. This is called apparent viscosity. Right. So, today we have then discussed about the types of non-Newtonian fluids or even Newtonian fluid, and the relation between the shear stress and shear rate for this type of fluids, power law equation, Oswald-Day-Weyl equation. So, this we complete today here, and next day we will continue for the following aspects, following subjects rather. I should say that it will take some time rather to cover up the entire non-Newtonian fluid flow. Okay, thank you.